Hello. Dr. E coming in with a minute late stream to make up for going over class time. See, I thought it through. Hello, Pika. Hello. That guy who stinks says, time to get stinky. Good morning, D Stratus. It's Wednesday. 'Tis a beautiful day today in Buffalo. Yeah, it is. Yesterday was amazing, and today is just as amazing. Belkit says, will you have time for a homework question at the end of class today? It's a quick one. Yes, I will. I have to run soon after class because I'm going to this freshman mentor thing with Bill Wild, but I think, so that's at like 1:40. It's Wednesday, my dudes. Hey, Ando Bear. Hello, Nookus. Yo, Kate. Alright, let's jump right into it. Yo, we love 202 mentors. Are you doing that this year, Kate? I know you've been a part of that. Are the homework solutions going to be posted? Yes. I realize I got a little behind on that, so I'm sorry. I just got smashed with stuff. I mean, I didn't get smashed. I need to find another way of expressing that. I got very busy and that I fell behind on that. Okay. Hulk smashed. Smacked. Oh, good grief! You got smashed? Same. I do appreciate you guys. Alright. I saw a funny post today that was like, you think seasonal depression isn't real until it's 50 degrees and you feel like... yeah, it's you can tell, like, just the sun coming out, it makes a huge difference for your mood. Oh my gosh. It's true. Is this the same sheet from Monday? It's different. I mean, the top of it is the same, but it's gonna change. Literally, I'm out there like a dog sniffing the wind. Okay, let's review a little bit to just say, to catch up on where we are. So we're doing control of a DC motor, and we have our feedback diagram, and this is our model for the motor. This is our transfer function in the Z domain. And a transfer function in the Z domain, you have to give the associated sample period with it. And then we came up with a controller that eliminates steady state error. And it looks like this. It's got a control gain in the numerator, and then Z minus 1 in the denominator. Ando says, I just realized I can open my window. It's such a nice day out there. Okay, and just to summarize, if you look at transfer function number 4 here, it's called the closed loop output error transfer function. Basically, it's about the dynamics of our error over time. And what we found out is this. And this is how we came up with our controller. But if the product G of Z and D of Z, so this is called our open loop transfer function. If this has a pole at Z equals 1, the steady state error for a step reference is going to be 0. So we found this out by applying final value theorem to transfer function number 4 over here. So we came up with this result. We have to have a pole at z equals 1. So the open loop transfer function has to have a pole at z equals 1. The way we did that is we took our controller transfer function and we just added a pole at z equals 1. All right. Okay, just a little more review here. Let's show how this mathematically happens. So right here is the steady state error for a step reference. So this is the limit of the error as k goes to infinity. This right here is just final value theorem. And if you follow through the math, you get this. The limit of z approaches 1 over here. And we made a definition just to kind of simplify this. So we call this 1 over 1 plus kp. Kp is called the static position error constant. And if this expression is equal to our steady state error, if we want the error to go to 0, then kp has to go to infinity. And if you compare these two expressions right here, kp is the limit as z approaches 1 of g of z times d of z. So why don't we calculate this for our motor and just demonstrate once again that this is, it goes to infinity. So we're going to say kp is the limit as z approaches 1 of g of z times d of z, which is 1 point, so this is g of z, 1.796 over z minus 0.5134. And then this is our controller d of z. And you can see here, if I plug in 1 right here, that denominator is going to go to 0. And this is indeed going to go to infinity. Okay. And so where we left off is, let's see, we added this controller, we picked a gain. I think I liked this one, I can't remember. Let's plug it in. Let's take a peek at it, and then we're going to try another type of reference signal. We're going to try a ramp. Okay, it's the mega. Get the port correct. Upload this. Wait, is everything plugged in? F. What's going on? You saw it spinning for a second there, right? Effing heck! Is this week's material going to be on the test? No. I feel like... Oh, it wasn't plugged in all the way. Alright, let's just open this really quick. Okay, so the green line is the angular velocity of the motor. The blue line is the reference angular velocity. So this controller is giving us 0 steady state error. Okay. So now, what if the reference signal is a ramp? So this is what a unit ramp input is defined as. So it's k times t for k greater than or equal to 0, and it's 0 before. Loose connections are the main cause of the biggest headaches in the entire universe. Yes, I agree, especially today. Okay, so we're going to plot r of k as a function of k, and at k, so it's 0, 1, 2, 3. So at 0, r of k is going to be 0. At k equals 1, r of k is going to be t, because it's k times t. And then at k equals 2, we're going to be at 2t, and it just goes on in this linear fashion, and that's why we call it a ramp. So this is the reference we're going to try next. And we're going to try to look at the error as we're tracking this ramp. So let's draw what our motor is most likely going to do if it works. It's going to try to track the green line. But if there's some steady state error, it'll never totally catch up with it. I mean, our goal is to precisely follow that green line, but spoiler, we're going to have a little bit of error. But we're going to talk about how you could get rid of it as well. Forgive me. I forgive you, T. Jackson. I forgive you. But what are the effects of choosing a different gain? The effect of choosing a different gain moves around the closed loop poles. Actually, I'll pull this up really quick. So, what we did at the end of last class is we did a root locus plot, and this is showing where the closed loop poles for your system go as you change the gain, k. So when the gain was 0, we had 2 poles. One was here and the other one was here. When we chose the gain to be 0.033, both of our poles coincide right here on the real axis. So changing your gain moves around the poles, and we know that depending on the location of these, you can have like overshoot, different settling times, whatever. So that's what that does. Okay, so we're going to need to take the z transform of this of this ramp input, because we're going to use final value theorem. So if I'm going to take the z transform of this ramp, this is what you get. It's t times z over z minus 1 squared. So we're going to use this in a second. All right, so now we're going to calculate the steady state error. So the steady state error is the limit as k goes to infinity of our error, ek. And then this is the final value theorem right here, which just says that you can calculate this error by taking the limit as z goes to 1 of z minus 1 over z times your error in the z domain. Okay. So we'll keep working this out. The limit is z goes to 1 z minus 1 over z. So our error in the z domain, we're going to use our transfer function number 4 up here. Up there, which you can't really see. But it's e of z over r of z is 1 over 1 plus g of z d of z. So actually, I'm just going to write it like this first. We're going to take that transfer function, and then we're going to multiply it by r of z. And this is r of z, by the way. The z transform of our input up here. That transform is from last week when we were doing some magic, right? Yes, that's correct, Meerkat. That's just one that we're just going to use. And its origins are magical. Okay. So let's keep writing this thing. So e of z over r of z is 1 over 1 plus g of z d of z. And then r of z, we're going to substitute this in. tz over z minus 1 squared. And some things are going to cancel out here, fortunately, like this z can cancel with this z, and this z minus 1 can cancel with one of these z minus 1s, because that's a z minus 1 squared. And then we're going to be left with this. 1 over 1 plus g of z d of z times t over z minus 1. And here we're going to introduce another definition. So this, by definition, is equal to 1 over kv. So that just means, if you examine those two lines, like kv must be equal to the limit as z approaches 1 plus g of z d of z z minus 1 over t. And so we just define this term to just simplify this expression a little bit, so we don't have to write this whole thing out all the time. We'll just write it as 1 over kv. And kv has a name. It's the static velocity error constant. And people will use this when they're describing performance specifications for a controller. So they might be like, I need a settling time less than 1 second, an overshoot less than 20%, and I need a kV of less than 5 or something like that. So this is going to be another performance constraint that we're going to have in our toolbox, and this is a steady state error performance constraint. So we're actually going to have multiple types of performance constraints that we work with, like settling time, overshoot, rise time. Those are called transient performance techniques. But these static velocity, static position, these have to do with the error as time goes to infinity. So we call those steady state performance constraints. Okay, so we'll just point out one thing here. If I'm trying to track a ramp reference like this, and if I want the error to go to 0, so if I want to finally line up with that green line, then kV must be equal to infinity if I want to perfectly track a ramp reference because the error is equal to 1 over kv. So if I want the error to go to 0, I need to be dividing by infinity to drive that to 0. And this is going to be pretty easy to remember because remember kp must be infinite to perfectly track a step reference. At least at steady state. Like at steady state you approach you have 0 error. Okay, so what I want to do right now is I want to use our existing controller for the DC motor, which is this. D of z is just k over z minus 1. That's what we're working with right now. I want to calculate what this steady state error for a ramp reference is going to be, and then we're going to go over to the actual hardware and see if the error that we predict using math is what actually happens in real life. And I think it should be pretty close in this case. So, okay, so what we're going to do, let's calculate the limit of the error for tracking a ramp reference for our current controller. So d of z is k over z minus 1. And so the way we're going to do this is I know that the limit of the error is 1 over kv. And so we're going to calculate kv, do 1 divided by whatever that is, and see what the error should be. So kv is this. It's 1 plus gz d of z times z minus 1 over t. The limit as z goes to 1. All right, so let's start plugging stuff in because we know what g of z and d of z are. So it's 1 plus 1.796 z minus 0.5134. Let's fix that 9. K over z minus 1 times z minus 1 over t. What I'm going to do, are there any other references other than ramp and step? Yes. Really, a reference can be anything. It can be some really bizarre function. It could just be like random noise. But we have, yeah, it could be a sinusoid. That's another really typical one. But the reason we have these, like, we have something like a step and a ramp is that you could think of these as like Lego pieces that you can build more complex references with. So if you know how your controller performs with like a step and a ramp, you might have some idea of how it will perform with something more complex that could be built of steps and ramps and so on. Okay. What I'm going to do, I'm going to turn this 1 into the ratio of z. I'm going to make it z minus 0.5134 times z minus 1 divided by that same thing. So, okay. So we're going to end up with z minus 0.5134 z minus 1 plus 1.796 k divided by 0.5134 z minus 1 times z minus 1 over t. How do we approach the other ones? Cautiously. That's good advice. We'll get to it. Patience, D Stratus. Okay, notice these z minus 1s are going to cancel. And then if I take the limit as z approaches 1, plug it in here, I'm going to have 1 minus 1 at 0. So this whole term is going to go to 0. And it's going to be 1.796k divided by 1 minus 0.5134. So I'm plugging in 1 for z down there. And then I'm going to multiply this by 1 over t. And the gain that we chose right now for our controller, I mean, we can always change it. It's 0.033. Okay, let's calculate this. 1.796 0.033 divided by 1 minus 0.5134. I probably have too many parentheses here. You probably don't need this many. And then I got to divide by t, 0.05. So this is our kV. (2.436). And then our error, our steady state error, is going to be 1 divided by this. 0.41 radians per second, I guess. So kV is 2.436. I just put a dot 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 in the numerator here, but it's just continuing this. And so the limit as k approaches infinity of our error when we have a ramp is 1 over 2.436, which is 0.4105 radians per second. Now let's go to the Arduino. Let's input a ramp input. And we're going to have to build this code on the fly here. I don't think it'll be too crazy. I think I have a ramp input code hanging around, but okay, RK, RSS. Okay, what we're going to do, we're going to copy this, we're going to comment it, and now we're going to unit ramp reference. We're going to make it right here. We're going to say RK wait a second. So every time we go into this loop, okay, we're gonna do this first. RK, it needs to increase by t radians per second each time. So this will start at 0. We're going to start at 0. So up at the top of the code, our reference is going to start at 0 angular velocity. All right. And then, but I kind of want to make a triangle wave out of this. Because if I just have the reference increasing always in the code, it's going to get pretty quick. Heck, let's just run it. Let's just run it first. We might turn it into a triangle later, but I think this will do what I want it to do. And this is the same controller. Okay, we got to try it. We have to try this. And remember, when we're looking at this, wait, wrong one. We want to see if the error approaches 0.41 radians per second. So you should be looking at the difference between these lines. Okay. Come on. And what are we plotting? We're plotting, oh, I want to plot our K. So this is going to keep going up. This is going to be our voltage, and this is going to be our angular velocity. Let us do it. Come on. And if it doesn't work, we're going to blame it on that guy who doesn't stink. Okay. Let's plug this in. Okay, so it's starting. The blue is the reference. We're going to reach maximum speed here in a little bit. This is the voltage, by the way. The voltage source only goes up to 6 volts. Wait, what the cats? Okay, so we reached terminal velocity here. Let's do that again, but look at the. Let's do that. What is going on? Let's look at the serial monitor view this time. So we're just going to look at some numbers. To infinity and beyond. Okay, so the first column is the reference angular velocity in radians per second. And this is the actual angular velocity. Wait, I have an idea. Okay, let's stop this. What I want to do, I want to copy this data. And then I'm going to load it. Does the serial plotter have a legend? It does look like they're within 0.4. I think you're right. First column minus third column. Wait, text. Notepad. Let's save this as our ramp test. Ramp test 3/10/2021. Wheel falls off. Yeah, we were kind of pushing it to the limit there. Wait, okay, so I want to say data is load ramp test 3/10/2021.txt. And then the first column is going to be the reference, and then the third column is going to be the actual output. And then I have to save this in the same folder. Ramp test analysis. I think this is in the same folder. Wait, is it? Oh, what? I'm a. Okay. Okay. What I want to do is I want to plot this. And I want to do like the error is r minus y. And how about we plot... Oh wait, T... Oh wait, this is the third... T is the second column, right? Or no, that was voltage. Okay, T... N is length R. T is 0 with 0.5 second increments up to n minus 1 times 0.05. So I should be able to plot T, R, T, Y. Let's try. Oh, here it is, here it is. Now, Now. Let's plot the error. Okay, what if we take the mean of the error, but like it looks like it after 12 seconds here, it was kind of getting out of control. So what I'm going to do is I'm going to take the mean of the error, but for indices. So I'm going to find the indices where t is less than 12. Is that going to work? Let's just run it. I don't know if the syntax is right. 0.37. So that's like the mean value of the error. Wait, does that make... I guess it is. Like if you zoom in here. All right, what did we calculate the error was going to be? .41 radians per second. Hey, I'm pretty happy. Our experiment has, let's just say like the mean of the error is like 0.38. So pretty close. And the signal was pretty noisy anyways. So let me ask you this. This is not an easy question. But how can I revise my controller to make the error go to 0? That's my question to you. And I think maybe, so we listed a condition before that KV must be infinite, right? In order for the error to be 0, because the error is 1 divided by KV. But if you look like 3 lines down here, what did we need here for this to go to infinity? What would we have needed? Add another pole at z equals 1. Yes. You guys are exactly right. If you added, because this is the limit as z goes to 1, if we could have just had another magical z minus 1 here, the error would go to, I want to go to negative. Don't say that. Okay, so if we had that. So, if we just, so like a very quick way to maybe do this, kind of like what we did last time. What if we revise d of z so that it's like a gain, but then we have z minus 1 times z minus 1? Don't say the number who shall not be named. And I haven't played around with this yet, but remember, d of z is u of z over e of z. So this would be k times e of z is u of z, z minus 1, z minus 1. U of z, z squared minus 2z plus 1, right? Chat should ban the phrase negative infinity. so I have... What I'm trying to do right here is make a difference equation. Because I want to see how would I have to revise my code to implement a controller like this. So this would be z squared u of z minus 2z u of z plus u of z. So k times e of z is equal to this. And then I want to use backward shifting theorem. We wouldn't even... Yeah. And then, so I want to use backward shifting theorem. So I'm going to multiply both sides by z to the minus 2. So I'm going to have k z to the minus 2 e of z equals u of z minus 2z minus 1 u of z minus z minus 2 u of z. Okay. And then, if we bring this back into the difference equation domain, using backward shifting theorem, I would have k times e k minus 2. So you need the error from 2 time steps prior. And then this term is just going to be uk. This is going to be minus 2 uk minus 1. And this one's going to be minus uk minus 2. So here's going to be my revised line of code for this controller. U of k is equal to 2 uk minus 1 plus u... Oh wait, I need a plus sign here. Why did that last value go negative? Okay, thank you, Meerkat. That's right. Okay, plus. So this has to be minus uk minus 2. Plus k times ek minus 2. All right, so maybe we'll come back to this. You'd have to do a root locus analysis in order to pick what that gain k should be. Because if you just throw some number in there, you might have an unstable system. So you have to look at where the roots would end up in the z-plane. But I want to show you this to kind of just show you the line of reasoning that we do when coming up with control laws. This is an example of like, okay, if I want 0 steady state error on my ramp, what is practically what I need to do? Well, I know I need to add another pole here. And then you just follow the math and it gives you your line of code. Okay. So before we do anything with that, I want to come to this table and we're going to talk about system types. Because this is lingo that you have to know for controls engineering. And this all has to do with classifying, like knowing what kind of steady state error you're going to expect for a given system. And it has to do with the number of open loop poles at z equals 1. So the first system type is system type 0. And then we're going to do system type 1 and system type 2. And I guess you could even go to like type 3, 4, whatever. But these, typically we stop here. And it's easy to remember because the system type, it just goes back to the number of open loop poles at z equals 1. So a system type of 0 has 0 open loop poles at z equals 1. Remember the open loop transfer function is g of z times d of z. So if I have a model for my plant g of z and somebody tells me, hey, this is the controller I'm using d of z, you could look at their function and be like, hey, how many open loop poles do you have at z equals 1? If they don't have any, then the system type is 0. If they have 1, then the system type is 1. If they have 2, the system type is 2. So these last 3 columns over here, this gives you the steady state error for different types of reference signals, a step, a ramp, or a quadratic. So if you have a type 0 system, the limit's going to be 1 over 1 plus kp. That's just the general function. And if you have a type 0 system, meaning you don't have any open loop poles at z equals 1, this is not going to be equal to 0. So I'm putting like not equals. And it's going to depend on whatever non-infinite kp value you have. But if you have one open loop pole at z equals 1, you have 1 over 1 plus kp, but remember this makes kp go to infinity, so the error is 0 for a step. So this is the type of controller we have right now. We have a type 1 open loop system. And then if you had 2 open loop poles at z equals 1, actually like what we've defined over here, this would be a type 2 system. 1, 2. So this will also have 0 steady state error for a step. So if you have a type 1 or higher system, it'll have 0 steady state error for a step reference. What about a ramp? It turns out, well, okay, we showed a type 1 system. Like our formula is 1 over kV. And this wasn't equal to 0. It was equal to like 0.4 radians per second for our system. But if we made our system type 2, kV would have evaluated to infinity, and it would be equal to 0. If you have a type 0 system and you give it a ramp reference, the error is infinite, because what happens with a type 0 system, maybe I'll come like down here, you're going to have a ramp that looks like this. What happens with a type 0 system is you fall farther and farther behind. And that's why as the steps go to infinity, that difference just keeps growing, and so we say the error is infinite. Okay, and then let's finish up this column. Quadratic reference. So a quadratic reference is, instead of linear, it's like an x squared kind of relationship. And you're trying to track this. If you have a type 0 system trying to track this, same thing's going to happen. You're going to fall farther and farther and farther behind. If you have a type 1 system, it's also going to fall farther and farther behind, but it'll do a little bit better. So this is going to be infinite. If you have a type 2 system and a quadratic reference, there's actually a k sub a, and that's called the static acceleration error constant. And you would follow this and you would converge to like some constant gap in between. So when you think of system types, the higher the system type is, like 2, 3, whatever, you could think of your controller as being more agile. It's able to track more faster changing references. Okay. And guys, that's where we're gonna stop here today. Type is same as order? No. Type is not the same as the order of the system. The system type, the simplest definition is the number of open loop poles at z equals 1. So this is totally independent of the system order. So system type is this. Because you could have a high order system that doesn't have any open loop poles at z equals 1. And it might actually have terrible steady state error. Why is it at 1 specifically? Well, to show that, you have to go back to last time we did a little proof. Is that Ka for the last? Yes. Yeah, this is Ka. It's kind of like you have Kp, the static position error constant. You have Kv, the static velocity error constant. And you have Ka, static acceleration error constant. And we're mainly going to stick with these two in this class. What are the downsides to a large number of open loop poles at z equals 1? There's one downside. This is not a huge downside, but this depends on information from 2 time steps prior. Yeah, so that's kind of what I'm getting at. What Not in Space is saying is that you have to store more and more variables on your microcontroller. Like if I had a type 3 system, then this is then going to depend on error 3 time steps prior, and so on and so on and so on. Excuse me. But that's not like a huge detriment. Will you be uploading the rest of the filled in notes on UB Learns? Yes. Yeah, I'm going to upload all the notes that I've done so far. Is Z-transform, backward shifting theorem, and all that on the midterm? No, the midterm is on homeworks 1 through 3. Okay, Belkit has a homework question. On homework 3, how much % error are you looking for when considering overshoot? Also, what are some things you were looking for in the brief justification? So I know people have been mentioning in the Discord, and I've gotten some emails that the rise time error, they're getting errors like 10, 20%. I was getting the same error. Right now I don't have the best explanation for that, and I'm still looking into it. My gut tells me if you increase the sampling frequency, like the sampling frequency that we're dealing with is pretty slow here. I think if you increase the sampling frequency, the error would decrease. But it doesn't really... I kind of thought that it would be independent of the sampling frequency, how well it does with rise time. Overshoot... You might encounter a similar amount of error, but I feel like that should be a little bit closer. You didn't get rise time error, just overshoot error? Okay. But yeah, in general, if you're running into like maybe 10, 20% error, don't worry about it. What time will the midterm be uploaded and what time will it be due? Any ideas yet? I'm going to try to get that information to you. Like, at the latest, the information will be to you on Friday. My best guess is that I'm going to post the test at 10 a.m. on Saturday morning and have it due at noon on Sunday. That's my current plan, but I'll finalize that this week. That guy who does not stink says, do people ever consider to increase error and avoid the reference rather than limit the error? Wait, do you mean... Wait, are you saying do people make it a goal to make the error bigger? Oh, I think I see what you're saying. Like trying to create a tag problem where maybe you're always trying to stay as far away as possible from something. That's interesting. I bet there's some application for that, which I haven't really thought about. Exactly what I'm thinking. Yeah, I mean, you could use these same principles to try to but that wouldn't really work with this, because like if you're trying to be agile yourself in avoiding something, the error that we're talking about here is happening because your controller basically isn't agile enough. So I think if you were like really trying to make a device that can like play keep away or something, you might want to maximize error, but you would do it in a different way than what we're seeing here. In this class, we're considering undershoot to be overshoot. For problem 3, my recursive solution was within overshoot range for the undershoot, but no overshoot. Yeah, because for this homework, I made it so that we're just looking at the homogeneous solution starting at 1. And so it's just going to go down and undershoot. And that's what you should be using for the for checking the overshoot condition. Because how much it undershoots in this case is how much it would overshoot if you had a step reference. It's cheaper to produce at higher error. Yeah, I think generally better performance on a controller is more expense. Okay, guys. I have to run. I have to go to another meeting. I'd love to hang out more with you guys. So Friday, my plan is we're going to do a test review. We'll probably make like a flow chart, because I like flow charts. For the question 3, I keep selecting routes within the shaded region that should meet criteria. They meet all the overshoot. They meet all but the overshoot each time. Well, think about it. Like, if your overshoot isn't... If you have too much overshoot, you can always... What am I saying? Let's go back here. Okay, you see these contours? Like the ones that are shaped like a sideways heart? The overshoot gets smaller the more you move towards the center here. So if you have too much overshoot, you can always scoot in like a little bit and like keep moving a little more towards the center. For choosing the routes, I know we're able to find the natural frequency and damping ratio from the Z-grid. I'm just confused on how to choose the lowest order system. Yeah, increasing damping reduces overshoot. Well, like when you're talking about the order of a system, we're only looking at first and second order systems. A first order system will have one real root, so it'll be a root on the real axis. A second order system will have a complex conjugate pair, or it could have 2 roots on the real axis. So if you want a first order system, it has to be... Will there be homework solutions posted before the exam? Yes. Yeah. It'll definitely be up before the exam. Second order will be it could be oscillatory. Because the second order can be 2 real roots as well. It doesn't have to be a pair of complex conjugate. Hey, happy Wednesday, Pika. Thank you. See you guys on Friday. Yeah, we'll do review on Friday. We'll talk about the exam. We'll answer questions. Hey, have a good one, everybody. Oh wait, is the exam something like when you open the exam you have 2 hours to complete it? No. I'm going to design it to be like a 1 or 2 hour exam, but you have the full time to work on it. All right, everybody.